Hi, everyone. My name is Hillary, and I'm ARM's Sustainability Strategy Director. My job is to help us deliver sustained and sustainable growth for ARM and our wider ecosystem by applying what we do best to help solve some of the world's most complex challenges. So, the climate crisis is one of the greatest challenges facing humanity right now. We must reduce greenhouse gas emissions by 45% by 2030 and down to net zero by 2050 to avoid catastrophic climate change that we're already seeing the impacts of today. At the same time, the world has digitalized overnight, yet 3.7 billion people remain unconnected. That means they're unable to access the basics, such as healthcare, finance, education. The pandemic has definitely made the situation known as the digital divide much worse. The need to decarbonize our economies is in conflict with the processing needs of the world and the expectations as compute grows. ARM brings low power compute into the world, and in doing so creates opportunities through our partners that would not have been possible otherwise. So we really have the responsibility as well as the power to really address this tension. So therefore, the two focus areas of ARM's sustainability strategy is to decarbonize compute and close the digital divide. Our aim is to extend the reach of our technology through our partners to where it's needed most in order to enable progress, and in doing so, unlock new markets, opportunities, and applications from a commercial perspective, whilst at the same time driving down associated carbon emissions by accelerating the deployment of highly efficient, low-power compute into the world as we increase performance per watt. ARM is very much committed to helping the world achieve the United Nations Sustainable Development Goals by 2030. So these are 17 interconnected global goals. World leaders from 193 nation states have agreed to, with the aim of creating a better world by 2030. So this is very much looking at things like ending poverty, fighting inequality, and of course, urgently addressing the climate crisis. And so our strategy at ARM, by closing the digital divide and decarbonizing compute, we can really empower more people to make gains across all of these goals as they are able to access information, opportunities, and the tools to become a part of the solution themselves. So that's a bit of the why in terms of what we're really trying to achieve here. And when we kind of double click into the decarbonized compute side, efficiency was a necessary requirement due to ARM's origins in mobile. That's something we've always focused on, and some would say it's part of our DNA. How we leverage this leadership to optimize further than ever before with carbon reduction as a driver for innovation, so turning it around on its head instead of just an outcome. Now knowing what we know about the climate crisis, how do we make sure that we're intentional and focused around it? And who better to ask to start exploring this challenge than our leaders of tomorrow? So at ARM, we have the Young SDG Innovators Program. It's a 10-month accelerator where teams tackle a genuine business, social, environmental, economic challenge while developing the skills around business model innovation, sustainability, and disruptive technologies, with opportunities to really collaborate with senior leaders to drive meaningful change through new ideas, new processes, and just ways to create value for our ecosystem in this current context of a much more volatile, uncertain, complex, and ambiguous world that we exist within. So ARM joined this program in 2019 with our first ever cohort, and the outcome of that work resulting in sustainability metrics being integrated into our research processes with great success. So with that introduction, I want to turn it over to Hannah, who is part of our US YSIP team this year, to tell you a little bit more about what they've been up to in hopes of inspiring all you change makers out there.
Our US YSIP team is very excited to share our work with you today. In our team of three, we have Zach Lashik, a solutions designer at ARM, who unfortunately could not join us for this talk. Speaking today are the other two members coming from ARM Research, myself, Anna Peeler, and Joshua Randall. For our project, we wanted to tackle the large and prescient issue represented by global goal number 13, climate action. A core target behind goal number 13 is to reduce the amount of carbon emissions humans have been increasingly pumping into the atmosphere for decades. An activity that, as shown here, has been and will continue to increase the surface temperature of the Earth by unprecedented amounts. We have to reduce our carbon emissions to limit further temperature increase and its effects. This is a Herculean problem requiring innovation and contribution from all manner of communities, industries, and companies. This especially includes the information, communication, and technology industry, or ICT industry, that many of us are members of. ARM has already made a commitment to achieve net zero carbon by the year 2030, 20 years ahead of schedule for the target outlined by the UN Paris Climate Agreement. This goal will be achieved using a collection of core activities, ranging from renewable and responsible energy procurement practices to supporting innovation in tech-based carbon sequestration solutions. Two of the core activities in ARM's strategy include engaging with our supply chain to set sustainability procurement targets and empowering our people to make low carbon choices. Both of these goals complement very nicely with our own goal to reduce our emissions by 20% very soon. We made great strides in taking science and data-based approaches to these goals, but the reality of integrating carbon reduction into our everyday design activities has proven to be a difficult hurdle to overcome. There is desire to operationalize carbon reduction across the business, and today we discuss a way to bridge the gap between our current difficulties and that vision.
At ARM, we are quantifying our overall emissions to meet carbon neutral goals. But we need to take this a step farther, zooming in on where our emissions come from to find opportunities for reduction. Components of our carbon footprint include business operations, compute for our design processes, and compute in our verification activities. Our team set out to quantify opportunities for carbon reduction and operationalize a methodology for evaluating emissions. For example, we could evaluate data center hosting choices for lower compute footprint. Additionally, estimating carbon could inform efforts to streamline our verification processes. Our team's vision also includes quantifying opportunities for our IP to influence emissions throughout our value chain, including our technology partners and end users. These reduction opportunities could take the form of more efficient ARM systems or improvements to reliability. Our team chose to initially focus our efforts on studying data center emissions because this gives us the opportunity to evaluate both our internal processes and the footprints of our products in the industry. Internally, we use data centers for our computing needs, and our products are a component of the industrial data center footprint. Data center usage, and thus share of carbon emissions, are shifting towards cloud and hyperscaler providers. It is more important than ever that these providers have resources necessary to lessen their environmental impact. We will dive a bit deeper into how this increased demand has been handled thus far and what approaches are needed for the future.
While the ever-increasing demand and importance of cloud and hyperscaler providers drives up their proportion of global data electricity use, the opportunities to maximize benefit while also minimizing carbon emissions does as well. Great achievements have been made thus far to limit carbon emissions increase even with massive growth. Up to this point, the strong growth in demand has been offset by ongoing efficiency improvements in technology. On top of that, the ICT industry is a leader in procurement of renewable energy, accounting for 50% of the global corporate renewables procurement from 2014 to 2019. All of this has meant that carbon output for the industry has remained steady, but efficiency improvements have begun to slow in some areas and do not come as easily as they once did. As efficiency improvements become harder and harder to attain at a breakneck pace, demand increase is not slowing down. By 2025, it's estimated that there will be 25 million IoT connections and 5 billion mobile users, a large amount of which will rely on data center resources to support their needs. With 4.2 zettabytes per year of data flowing into data centers and increasing internet use, we need to tackle the carbon impact of all this activity directly. This is made even more poignant when we remember that not even renewable energy comes free of all carbon. It cannot be available all the time, meaning that 100% renewable procurement does not equal zero carbon. We need data-centered approaches that give us a clear view of the carbon cost of our activities, so we can use that information to bridge the gap to lowering carbon emissions. There are many factors we need to consider when evaluating data center emissions in specific. We have grid carbon intensity, which is a measure of how much carbon equivalent and global warming potential the electricity mix of your power supply is. This will be higher or lower depending on the sources of electricity available and used. All physical resources also have embodied carbon emissions resulting from their manufacturing. For a given facility, how the space is utilized can have a profound effect on its overall carbon impact. Of particular interest to our work is the server hardware power efficiency and how the nuances of this specific factor affects carbon emissions at scale. What hardware is used, how it's used, and how it is organized can make a huge difference. Related to the hardware is the power usage effectiveness itself. For every unit of power that results in usable output, there is always some that is expended without benefit. The lower this ratio is, the better. So you see, this is a multifaceted problem, which reflects its complexity, but also the myriad opportunities for good discretion to lower carbon emissions. The vision for the future for not only data centers, but any area of the ICT industry is to create a comprehensive carbon cost model, covering as much of the supply chain as possible. For the data center, this means considering the different factors discussed thus far and even more. Many of these factors are not monolithic in and of themselves either. We can see for just 3 of these core factors, we can identify multiple component pieces, not all of which are listed here. This is a vision of a comprehensive model that will require a large, multidisciplinary, multi-company approach to be effective, but we have to start somewhere. To better illustrate what a data-centered comparison using a carbon lens like this would look like, let's zoom into a sample use case. We're going to explore hosting resources in the cloud that conduct primarily ML inference from 2 different perspectives. The first perspective is that of a user, say a developer or engineer that wants to run inference in the cloud, but does not want to maintain the resources themselves. From this perspective, there is a set level of work or compute that they want to accomplish, and they want to accomplish that with as little emitted carbon as possible by choosing their power setup and resources carefully. The second perspective is that of a cloud or hyperscaler provider, or even maybe an on-premises data center maintaining their own resources. Here, power is often procured ahead of time, and the provider wants to make best use of that power to effectively maximize performance per watt, and thus also performance per carbon. So let's start with the user's perspective. For a user utilizing a cloud service, we will discuss the parameters that are available for them to control and the effects those choices have on the amount of carbon emissions their solution would create through an equation framework. We have the type of instance and target workload fit for their purpose. This will change based on the provider, but this ultimately determines the CPU type underlying their resources, and the power will draw when serving their workload. This is shown here with monthly power draw per CPU and a performance adjustment factor that would normalize for performance when comparing against other solution options. There's also the size of the instance, equivalent to roughly the number of CPUs needed and number of instances as well, which multiplies the size and impact of the overall solution. There's also the expected duration of the use of the resources, another multiplier that brings us from dealing with power to actually dealing with energy now. And the last parameter that we will cover is the desired region or location of the resource, which determines the carbon intensity of the electricity used to power the device. All of this together can be used to calculate a representative carbon emissions amount for your solution. With this info, the carbon lens can be added to the process of resource allocation decisions to limit the environmental impact of the work we all do. Let's now look at the provider's perspective, kind of the other side of the coin compared to the user perspective. The parameters shown here are the same as what we showed for the user perspective, but are viewed really differently. Here, there is a combination of all manner of resource types, sizes, and number that create a fixed resource for the data center and factor into a fixed power envelope like we discussed earlier. We want to maximize total performance for a given workload within these bounds, and we represent this fixed value through a coinciding carbon cost envelope. The resources held by the data center determine the CPU composition of the solution. So that in turn gives us monthly power draw per CPU, used in the inverse here, the performance per CPU, and a conversion that brings us to energy once again. Finally, where the data center is located and how the energy is procured gives us our carbon intensity, once again used here in the inverse. Altogether, we can calculate the total performance possible within our power envelope. Really powerful information that can help inform future decisions of energy procurement, resource management, and overall data center design. Of course, how this information is packaged is important too. So we envision a solution that offers transparency into this equation, but displayed in an easy to use and understand tool. Our proposed tool aims to easily and transparently apply the carbon lens to different engineering decisions. Shown here is a still from our internal demo applying the carbon lens to a data center resource context. Someone using the tool, say a productivity engineering lead or a developer allocating resources themselves, would select what parameters represent their solution, including what primary local workload they're targeting and the amount or duration of the resources needed. The example here focuses on comparing solutions hosted either on the cloud or in some on-premises location. You can also compare different locations for the same provider, types of instances used, and combinations of size and number to explore simultaneously minimizing carbon emissions while maximizing performance. Not only are the results shown for the solutions being compared, but our solution will come complete with known caveats for each data point and transparency into how that data is used to get the result shown. Graph data views will come included that auto-populate based on the inputs chosen and give a quick, clear visual to compare solutions easily. We're already exploring how to expand and refine this concept to make it as effective and easy to use as possible. While our core example for this presentation revolves around the data center and their hardware resources, surely there are other areas of opportunity to apply the carbon lens. In fact, we have a couple more examples to share with you today.
The tool we have outlined provides an opportunity for us at ARM to view our internal process decisions through a carbon lens. When we decide what data center to use for our CPU development operations, we can evaluate the emissions impact of our choices. So how do we evaluate these options? Well, we can measure the emissions characteristics of our owned and our outsourced data centers, studying their efficiency for our computing needs. The most efficient data center choice may not be the same for every activity and workload. This analysis would reveal how to target them appropriately and improve our overall efficiency, reducing our carbon emissions. This type of evaluation illuminates options for immediate emissions reduction in our internal processes. Continuing to use emissions as a metric will lead to sustainable compute choices moving forward. Our methodology also provides data to motivate an IoT product use case. Consider a security camera processing video at the edge versus one that runs inference in the cloud. A more efficient overall solution will result in lower carbon emissions and operational costs. Offloading inference and processing to the cloud may lead to a lower power edge device, but this will incur significant transmission overhead, and inference will require processing in the cloud. Running inference in the device would consume more power at the endpoint, but reduce transmission and cloud processing overhead. Estimating the efficiency and emissions of each of these components will allow an overall comparison of the footprint of the two options. This will offer a cost reduction for the user of these products. A sustainable overall solution will provide value for conscious consumers. The two use cases we outlined here show how we can estimate the carbon impact of decisions. So how do we factor carbon into our decision-making process? A typical decision analysis will consider the end result and the cost of the choices. The end result includes the solution benefit and time to solution. And the cost can be measured in terms of time, products, and services it takes to achieve that result. Carbon provides a new perspective to evaluate the benefit and cost of options. Carbon reduction is becoming increasingly tied to cost through carbon taxes, carbon sequestration efforts, and carbon-conscious consumers. Efficiency improvements may also provide a win in all three of these areas, achieving better solutions with lower carbon emissions and overall costs. For example, when we streamline our internal testing methodologies, this leads to higher throughput and lower time to solution for our products, increasing productivity while reducing our compute resource costs and reducing the carbon overhead of these processes. Let's consider the components of costs when we optimize compute. When evaluating the cost of compute, we typically care about performance per dollar. Energy also factors into this cost model, and performance per watt must also be considered. We should also consider the cost of emissions, optimizing for performance per CO2 equivalent. This carbon perspective offers a more complete model to the cost of compute that we must take into consideration when developing sustainable technology. We need to optimize for perf per watt, perf per gram CO2 equivalent, and perf per dollar. Our team developed a data-centered methodology for evaluating carbon reduction opportunities. This approach will yield benefits both to ourselves and our value chain. At ARM, targeting emissions reduction will lead to greater efficiency of our internal processes. We will provide more performance per cost for our tech partners, and we aim to reduce the final cost for our end users. ARM is seeking to decarbonize compute by reducing our own emissions, as well as emissions from our value chain. We would like to know how we can help your efforts to develop sustainable technology solutions. Stay tuned to ARM Community and ARM Blueprint blogs, where you will provide more information on what ARM is doing in this endeavor. Feel free to contact us to discuss how we can work together towards reducing emissions and addressing climate change. Thank you for listening.